Regression analysis helps us to make predictions using a dependent variable and independent variable. And it's generally divided in two main groups of linear regression and logistic regression. Linear regression concerns problems where the dependent variable is mainly a continuous type of variable that has to be predicted. But what if your dependent variable is a form of a binary variable? For instance, a true or false, win or lose, a 0 or 1. In that case, you need to use another model, which is called logistic regression. For instance, you might want to know, was the treatment effective or not? Will a firm default or not? Or are patients receiving good care or poor care? The results of a logistic model is not a yes or no answer. Rather, it calculates the probability of the outcome happening. Classification analysis attempts to find variables that are related to a categorical variable. For instance, website users can be classified as the ones who click on an ad or don't click on an ad. Or clients of a health insurance company could be classified as being healthy or having a disease. Therefore, classification analysis attempts to find explanatory variables that help predict which of the two categories a customer belongs to. The logistic regression uses the log-odds ratio, and the odds ratio is a term frequently used in everyday language. The equation says that the natural logarithm is a linear function of the explanatory variables. Let's talk about what are the odds and how we can actually use them in business. Odds basically help us to find out if an event is more likely to occur as the predictor increases or decreases. When you run the regression model, if you find out that the odds or the coefficients of one of the predictors is more than 1, then in that case you could say the event is more likely to occur as the predictor increases. And if the odds are less than 1, then that means that the event is less likely to occur as the predictor increases. Suppose that you want to build a logistic regression model to predict whether a customer will churn or stay with your business. And you want to include a variable such as loyalty program membership, such that if someone is a member, they would be assigned a 1 and non-members are assigned 0. When you run the logistic regression model, if the odds ratio for the loyalty program membership is 60%, that means that customers in the loyalty program are less likely to churn compared to non-members. Since 60% is less than 1, that means being in the loyalty program reduces the likelihood of churn. And these two variables have an inverse relationship. So that's how you can interpret odds in a logistic regression model. Let's look at another example. Suppose that we have a study of 100 subjects with coronary heart disease. And what we would like to find out is if a person is more likely to have coronary heart disease or not, based on their age. So age in this example is the predictor, and having coronary heart disease is what you want to predict. If you basically just plot the instances as a scatter plot, you'll see that some people with different age brackets have the disease and they're denoted as 1, and some people don't have the disease and they're denoted as 0. In this example, these are the actual results. So based on the actual results, you can develop a logistic regression model with which you can then make a prediction of if a new patient would have the disease or not. However, if you want to fit a function for making this prediction, we actually cannot use a linear function, and that's why we can't use a linear regression. The main difference between linear regression and logistic regression lies on the function that is used. In the logistic regression, we can use a sigmoid shape to fit the data, whereas the linear regression uses a linear approximation. A sigmoid shape would take values between 0 and 1 range. However, the linear regression can take values outside the 0-1 range, and that's why it won't fit with the logistic regression outputs. Therefore, in order to capture that, you can use a sigmoid function. Now, let's go back to our example of finding the probability of a patient with coronary heart disease. When we run the linear regression model, the dependent variable is modeled as a binary variable. So what you want to find out is whether or not a person would be categorized as having CHD or not having CHD. And you can determine that using a probability. The probability would be calculated using this formula. And if you replace different age values here, it would produce different probabilities for different age groups. Suppose that the estimator of the logit provides the basis of this estimator, and using the equation, at age 50, the estimated logistic probability is 56%. But now the question is, how can we determine if this should belong to the 1 group or the 0 group? This is where you need a threshold value. The threshold value helps you to classify patients based on the probability value. What is threshold value? The threshold value is a threshold that is set by the modeler or the decision maker based on the goal. Now, suppose that you are indifferent and you don't want to basically have any discrimination. Therefore, in that case, you can set a threshold of 50%. 50% means that if any value falls above 50%, that would be classified as 1 or having CHD, and any value that would fall below 50% would be classified as not having the coronary heart disease, and 0. Because the output of a logistic regression model is a probability. But what you need to find out is if someone is classified as having the disease or not. Therefore, the probability always has to be classified as either 1 or 0. Now, let's look at another example. What we want to find out is if we have a certain goal in a healthcare organization, how can we use logistic regression model to find out if people are healthy or if they should be classified as having a disease? Suppose that we use two independent variables based on the historical data that we have that include the number of office visits and the number of narcotics prescribed. And what we want to predict is the healthcare quality, or if the person is diseased or is healthy. If they are diseased, we would denote that as 1, or the positive class. And if they're healthy, we would denote it as 0, or the negative class. However, in this instance, it's very important how you set the threshold value. The threshold value is often selected based on which errors are better. If we set the threshold value very large, then our model would predict the positive class very rarely. And in this case, the model would detect most people as being healthy and would put them in the 0 class. The error occurs because we may have false negative results. Therefore, here, false negative means that people would be falsely classified as being healthy, whereas they were being actually ill or diseased. On the other hand, if we set t as a very small value, then our model would predict healthy cases very rarely and would assign most of the cases to the diseased group. In this case, the errors occur because we say people are diseased, whereas they were healthy. And that would be a false alarm because you are classifying most healthy people as being diseased. However, if you don't have any preference between the errors, you can select t equals 50%, and that would predict the more likely outcome. That would help you to build your confusion or classification matrix. Any logistic regression model needs to be tested using the confusion matrix, where the accuracy of the model can be predicted and found. Looking at the confusion matrix, you can see that the confusion matrix would give you 4 different conditions. If your actual value was 0 and you predicted the value as 0, then you predicted it correctly as a true negative. And negative means having 0 or being classified as 0. However, if someone was classified as healthy, or in this case, 0, and they were actually ill, then you had a false negative because your prediction was 0, whereas they were actually diseased. So that's a false negative. On the other hand, you might have someone who is healthy, but your prediction was that they are ill. In that case, you had a false positive error because you falsely predicted that someone is ill, whereas they were healthy. But you may also predict someone who was ill as truly being ill, and that would be true positive. Therefore, your correct predictions would always lie in this diagonal, either true negatives or true positives that would base your true predictions or correct predictions. Therefore, if you add the true negatives and the true positives and you divide them by the total number of observations, that would be the accuracy of your model. Nonetheless, you should always pay attention to the sensitivity of your model. The sensitivity of the model measures the percentage of actual poor cases or ill cases that were classified correctly, also called the true positives. This shows you how sensitive your model was. You have another metric that shows you the percentage of actual good cases or healthy cases that were classified correctly. That would be the true negative rate. These two show you how balanced your model is. So if you find the average of the sensitivity and the specificity of your model, then you can find out how good and how balanced the accuracy of the model is. These two curves show you the cost of failing to detect a poor care and the cost of raising false alarms. Let's look at this accuracy curve. In this accuracy curve, you can see that if you increase the threshold after a certain value, you would not gain much accuracy. So if you increase the threshold above 30%, then you see that your accuracy doesn't improve that much. And after a certain point, such as 80%, your accuracy even decreases. That means that for this case, the accuracy is affected by the threshold, and after the threshold of about 35% or 40%, that's the maximum accuracy you would get. The ROC curve, on the other hand, shows you the true positive rates versus the false positive rates. And for the ROC curve, what you want is to have a bigger area under the curve. So the higher this curve is, it means that you were able to capture more positive rates, true positive rates. Therefore, the area under the curve is always assessed, and the larger that area under the curve, the better the power or the predictive power of your model was. Anytime you want to, therefore, find out which threshold value to choose from, you always also need to find out what is the cost of missing diseased cases and what is the cost of raising false alarm, and you want to have a balanced approach. In this case, I'm going to show you how your predictions would change based on the different threshold values that you could set. Let's look at the two extremes. First, let's look if we set t as 0. If you set t, or the threshold value, as 0, that means you would classify all the patients as having a disease or being in the 1 class. In that case, you've truly detect all the positive cases because you've assigned everyone, healthy or non-healthy, to the 1 class. But also you have 100% false positives because you've classified all healthy people falsely as being diseased. Therefore, your false positive rate would also be 100%. As you move along this spectrum, you can see that by increasing your threshold value, your true positive rates and your false positive rates change. And let's look at other extreme. If you look at t equals 1, what happens here is that you classify all the patients as being healthy. Of course, this is an extreme case, but if you set the threshold very high, near 1, you classify all people or all patients as being healthy. And that would mean that your true positive rates or your correct predictions are 0 because you couldn't identify any ill patients. Therefore, your true positive rates were 0. And your false positive rates would also be 0 because you haven't falsely classified anyone as being ill because you don't have anyone in your ill class or in your disease class or in the 1 class. Because if you set the threshold as 1, everybody would be classified as 0. Therefore, both of these would be 0. The best situation is to be somewhere in between and having a sensible threshold value based on the objectives of the organization. If the objective of the organization is to detect patients in the early stages and to have a conservative approach to healthcare and screen everyone before they develop any disease, then they might have to set a very low threshold. But if the strategy of the healthcare organization is to not raise any false alarms and detect cases if they are actually ill, then they might set higher threshold values. In that case, they would avoid having false alarms. And that's, again, something that is very, very objective dependent. So it depends really on what is the goal of the organization.